All right, so in the previous video, we were looking at how to find slopes of tangent lines and concavity and things like that with parametric equations, with curves given by parametric equations. So our focus there was primarily on the derivative. Now we're going to shift over and look at some ways of doing integration with parametric equations and how to interpret, different things involving the integral. So I'm going to move that down a little bit. Our next area, no pun intended, of study here is the actual topic of areas. When you introduce definite integrals at the end of Calculus 1, you talk about them in the setting of like areas under a curve. So for this, what we're going to do is assume that we have some curve. For temporarily, let's assume that the curve can be written in the form y equals f of x. Notice I'm using a capital F here because I'm going to use a lowercase f somewhere else. And let's suppose that the function is non-negative, so it's greater than or equal to 0 on the interval a, b. Then we know that the integral of from a to b of f of x dx tells us the area under that curve from a to b. Now you don't, when you talk about area and the definite integral in Calculus 1, you also say like this f doesn't have to be non-negative. It could go below the x-axis and give us negative values, and we interpret that to be negative area. But for the stuff we're doing here, we just want to think of area as a positive quantity, so we're focused on curves that are above the x-axis just for this. Okay? Now let's suppose that that same curve can be written in parametric form. So x equals some function of t, f of t, and y is equal to g of t. And let's suppose that t goes from alpha to beta. These two numbers here, alpha and beta, would take us to the endpoints of our interval a and b when we plug them into our functions f of t and g of t here. Then the area of this under this curve over that interval AB, which we said could be interpreted as this guy right here, can be rewritten this way. So that f of x is equal to y, so I can replace that with a y. I can think of that as the integral from a to b of y dx. But then this, when I make the appropriate substitutions, becomes this new integral. Y is equal to g of t, so we're getting that from here. And then remember, dx as a differential is the same thing as the derivative of x times dt. Well, the derivative of x with respect to t would be f prime of t because we have x defined to be f of t over here. So the dx becomes f prime of t dt. My limits of integration changed from a to b to alpha and beta here because, again, these are the parameter values that correspond to the a and the b here. You'll notice in square brackets over here, it says or, and then it gives this other integral where the alpha and the beta are switched. The reason for that is because t is going from alpha to beta, but it's possible that the smaller of these two parameter values when plugged into your parametric equations gives you the larger of these two values on your definite, interval on the x-axis. So again, it's possible that alpha is where we get b from when we plug alpha into our parametric equations, and beta could be where we're getting a from. It just kind of depends on the parametrization that you're using. We need the order of these parameter values to match the order of the a and the b here. So whichever of these values, whether alpha or beta, gives us a, that's the number that has to appear as the lower limit of integration, and whichever parameter value takes me to b on the x-axis is the one that I have to use as my upper limit of integration. So again, since that could go either direction depending on your parameterization, we're including this for reference. It could be one or the other. Let's look at an example here. Find the area enclosed by the parametric curve x of t equals sine of t, y of t equals sine of t cosine of t, where t is in the interval 0 to pi over 2, and the x-axis. So here I have a graph of this function over that interval shown for us. We have seen this parametric curve before. This was in the previous video, the one that had two tangent lines at the origin. And you may remember I drew kind of a picture of it. it looks sort of like a figure 8, but when we're requiring our parameter to only be between 0 and pi over 2, we only get part of that figure 8 shape. So this is the part that we're looking at. We want the area between this curve and the x-axis right here. So to do this, what we need is to think of this integral right here, which turns into this integral right here. In this case, the g of t corresponds to the sine of t cosine of t, and the x of t corresponds to, the f prime of t would be the derivative of my sine of t function. So we need to find the derivative of that guy first. The dx in this formula right here is going to be the derivative of this, which is cosine of t dt. So that's what the differential looks like when I change to my t variable. So that means the area is an integral. Now, when we shift things over to t's, the alpha and the beta that are appearing here are values for our parameter. They're t values. And we're actually given those in this problem. We don't have to figure them out by looking at a and b first. So I can just say from 0 to pi over 2 like this. Okay? Now the g of t, like I said, was the sine of t cosine of t. And we multiply that by dx, which is cosine of t dt. Since there's already a cosine there, that's going to become cosine squared dt. This is a straightforward integral to do with a u substitution. We can set u equal to cosine of t, so that du is equal to negative sine of t dt. I'm seeing the sine of t here, but I don't want it to be negative. So let's multiply both sides of this by a -1. That gives me that. This will give me negative the integral from u squared to u squared du. My limits of integration are going to change here. So again, u is equal to cosine of t. When I plug a 0 in, that's going to give me 1. And when I take cosine of pi over 2, that gives me a 0. Okay, I'll use that negative to flip the order of integration, or the order of these limits of integration. And I'm also going to just do the integral in this step as well. So I get u cubed over 3, and the negative's not making an appearance here because I'm going to use the negative to flip the order of these limits of integration. This would just equal 1/3. So that's the area of this little region shown here. Okay, that's that one. That's really all the time we're going to spend on areas because there's not a whole lot more to talk about there, just more examples that we could run through. We're going to shift over to the subject of arc length. So again, we talked about arc length back in chapter 8. 8.1 was the section where that shows up. So what we're going to do here is kind of build off of our previous result for arc length. We're going to suppose for a second that a curve C, or an arc of a curve C, is given by this function, y equals f of x, and we restrict x to some interval a, b. We're also going to assume f prime is continuous on AB. That was one of the conditions that we needed to be in place to use our arc length formula. Then from 8.1, we know that the length of the curve on that interval is given by this integral right here. Integral from a to b of the square root of 1 plus dy dx squared dx. Okay? Now, let's suppose that C can be represented parametrically this way. X equals f of t, y equals g of t, t goes from alpha to beta, just like in the area section that we did previously. We're also going to assume for this one that f of alpha gives me a and f of beta gives me b. And finally, we're also going to assume that dx dt is positive. I'll talk a little bit about that in a second. Well, at least positive on alpha beta, this interval here. We can make a substitution. Remember, what we talked about at the beginning of this section was that dy dx, when our curve is given parametrically, is equal to dy dt over dx dt. So this dy dx can change into this. Also, my differential dx is the same thing as the derivative of x dt times dt. We've used that also in this section. So the dx becomes this. If I wanted to bring this dx dt into this radical here, I could square it and then put it under its own square root so that those two things cancel out. So it's going to be like taking this into the radicand here and multiplying everything by a dx dt squared. That would cancel this dx dt squared in the denominator here, leaving me with dy dt squared, and then I would get a dx dt squared here, and this is what my new integral looks like. Notice that our limits of integration are from alpha to beta now because we're using t as our variable. So this is where this is what our arc length formula turns into when we look at parametric curves. Now I did make the assumption up here that our curve C was given as a function of x, and then we said, now let's shift over to a parametric version of that. But remember, that's restrictive because functions of this type have to pass the vertical line test. It turns out that this arc length formula still works for parametric curves that are not functions of x. So this is an example of one right here. This blue curve clearly fails the vertical line test in this area over here as well as over here. So this is not a function of x, but we could go through kind of a more detailed derivation of this formula here by taking our parameter interval alpha beta and breaking it up into subintervals, and then finding all of the points on this curve that correspond to the endpoints of those subintervals, and then connect all of those points with these line segments here. This is very similar to how we derived the arc length formula back in 8.1. And then we could continue from there, and we would ultimately end up with this exact same arc length formula, even for these more general types of curves. I do mention down here that if you're interested in seeing the proof for that, you can check the textbook. We're not going to go through it all here. There is an application of the mean value theorem that shows up in there, but that's going to be extra if you want to dig into that. So, I want to mention this before we do an example. It is important to note that this formula for arc length only works if your curve is traversed only once as t goes from alpha to beta. So as we saw in 10.1, sometimes a parametrization for a curve will have you traversing that curve multiple times. You remember we had that circle of radius 3 where we had a parametrization for it and it traced that circle twice. If you want this to work, then your parameter interval from alpha to beta here has to make that, it can only traverse the curve one time. Otherwise, you're going to be double counting that arc length or triple counting or whatever, however many times you go traverse that curve. So just keep that in mind. But now let's run through an example. So for this guy, we want to find the length of a curve given by x equals e to the t minus t, y equals 4e t over 2 to the power of t over 2, and t is in the interval 0, 2. So there's some ingredients to compute here. I need to find dx dt, which this one is pretty straightforward. E to the t minus 1 is what that turns into. I need dy dt. Whoops, I don't want a comma there. Also pretty straightforward. This would become 2e to the t over 2. Okay, then the thing that I'm integrating in my arc length formula is the square root of the sum of the squares of these. It's dx dt squared plus dy dt squared. Okay, so when I square these things, that's e to the t minus 1 squared plus 2e to the t over 2 squared. This will become the square root of e to the 2t minus 2e to the t plus 1. So that's this thing squared. Then when I square this, I'm going to get plus 4e to the t. Squaring it will eliminate that 2 in that denominator right there. I see a couple of like terms that I can combine here. So I get e to the 2t plus 2e to the t when I combine these, plus 1. And then this thing right here is a perfect square. That factors in a really convenient way. It becomes e to the t plus 1 quantity squared, which is super convenient because now I can use that to cancel the radical. This just becomes e to the t plus 1. Okay? So that is going to be what my integrand is when I'm doing my arc length. So now for arc length, we have an integral. Our limits of integration are the parameter, come from my parameter values here, by the endpoints of my parameter interval. So it's 0 to 2 in this case. Here's my integrand. We did all the work here to figure out what that needed to be. E to the t plus 1 dt. That is the same thing as e to the t plus t from 0 to 2. This becomes e squared plus 2. Then when I plug a 0 in and subtract, I'm going to get 1 plus 0, so minus 1 there. E squared plus 1 is my final answer. Okay, so that's the length of this curve on that parameter interval. All right, cool. You may remember in 8.1 we talked about the arc length function as well. We called it S of t, and what we did is we just took the arc length formula and we changed that upper limit of integration to a variable. So we called that t, which that also meant that we needed to replace the t's that were already showing up in our integrand with u's so that they don't conflict with the t that we're using here. They could potentially mean different things, so we don't want to cause confusion with that. This is called a dummy variable, that u, because once you evaluate this integral, it's going to go away. But S of t is defined this way, and remember what it does is for any parameter value that you plug in for t, it will give you the length of this curve going from alpha to whatever you plugged in. So this, if you take the derivative of this, from the first part of the fundamental theorem of calculus, differentiating a function like this with respect to t effectively just cancels that integral sign out and replaces all of these u's with t's, these u's down here. So differentiating that just leaves me with the integrand dx dt squared plus dy dt squared. But what does that mean practically? Like, what would be the point of differentiating that? Well, you can think of S of t as a position function, because again, what it tells me is the length of an arc from alpha to whatever we plug in here. So if you're thinking of this parameter t as time, and you think of that arc length as a distance traveled by a point moving along that curve, then if you wanted to look at a rate of change in that, you're looking at the rate of change in distance over time, which we interpret to be speed. So the derivative of this represents the speed of that particle moving along that curve. So we define that function here, but we're going to call it v of t. Now, normally v stands for velocity, but we're not going to call this velocity here. We're going to call it speed because we're not talking about a direction. Right, we're just talking about the actual numerical speed. If you go on to calculus 3, you'll figure out how to turn this thing into an actual velocity where direction is implied, but you need vectors in order to make sense of that. So we're going to call that our speed function. Notice there's no integral here. It's just this radical as it is. So let's try an example. Let's suppose that a particle is moving along a curve given by x equals t squared plus 1, y equals t to the fourth plus 2t squared plus 1. And we're going to suppose that position is measured in meters for this one. Time is going to be measured in seconds, so we have some units here. We want to find the speed of that particle when it's at the point 2, 4. Okay, so what did we need for this one? We needed dx dt and dy dt. So dx dt looks like it would just be 2t. dy dt we're going to get from that. That would be equal to 4t cubed plus 4t. And to me, that looks like something that just wants to be factored. So I'm going to write that as 4t times t squared plus 1. You can get away without doing that. It's potentially helpful to do that. So now what we want to do is come up with our velocity, or our speed function. V of t is equal to the square root of dx dt squared plus dy dt squared. Okay? for us, that's going to look like 2t squared plus this guy, 4t times t squared plus 1 squared. This is the same thing as 4t squared plus 16t squared times t squared plus 1 all squared, like that. Okay, and my gut, normally would tell me here is keep multiplying things out, keep simplifying. Maybe I can cancel that radical out at some point. But we actually don't need to do all of that for this problem, because that would usually be to make an integration step easier to do. But there is no integration step in this problem. So if we revisit what it is we're trying to do, we want the speed of the particle at a particular moment. We want it when we're at the point 2, 4. 2 and 4 are x and y values. I don't have any x's or y's here. I have a t here. So I need to figure out what parameter value t will give me that point right there. And this is typically pretty easy to do just by inspection. So what I do is I go back to my parametric equations here. Let's start with the x. X equals t squared plus 1. I'm looking for a value of t that I can plug into this so that x comes out to 2. It's pretty straightforward to look at this and see that 1 would do it. If I plugged a 1 in for t, 1 squared plus 1 is 2. Does that same parameter value give me this 4 when I plug it in over here? Well, you check. You say if t is equal to 1 on this equation, 1 to the 4th plus 2 times 1 squared plus 1, that does add up to 4. So it looks like we are at this point when t is equal to 1. That's what I want to plug into this. V of 1. Okay, so that's 4 times 1 squared plus 16 times 1 squared times 1 squared plus 1 all squared. And you go ahead and work all of that stuff out. What does this one come out to? It looks like it comes out to root 68, which you can simplify, but I'm going to leave that as is. And then because we gave units here, we're going to include units for speed, meters per second in this one. Okay. We have one more thing to look at in this section, but we're going to save that for the very last video.